All right, we are going to try to do two more quick graphs, but first I want to focus on this equation. It's actually the first thing we already put in our notes. Before you graph, try to simplify. And I hope you look at the top and you say that is definitely a difference of two squares. I can simplify it to x plus 3 and x minus 3. On the bottom, I see a trinomial. Anytime I see a trinomial, I try to factor it, and it is factorable to x minus 3 and x plus 1. So first, I simplify the top and the bottom. By doing that, you probably notice that the x minus 3's are going to cancel out, and that's true. But before we cancel them out, my question to you is 3 in the domain? 3 would make the bottom 0, so what does that tell you? That tells you 3 is not in the domain. So this idea of 3 not being in the domain becomes extremely important at the very end of this problem. When you cross off a variable like this, you have to be very particular of domain. At the end of the problem, I'll show you what I mean later. We're going to go through and find our four pieces: the y-intercept, the x-intercept, the vertical asymptote, and the horizontal asymptote. Starting with the y-intercept, you get that by doing g of 0, substituting 0 in for x, 3 over 1. Our y-intercept is 3. Our x-intercept, you get that by setting the numerator, the top, equal to 0. Without too much work, you get x equals negative 3. Vertical asymptote, you get that by taking the denominator, the bottom of the fraction, setting that equal to 0. You get a vertical asymptote at negative 1. And your horizontal asymptote pays attention to the degrees in the numerator and the denominator. Anytime the two degrees are the same, they are in this case, they're both 1s. You look at the leading coefficient, which are also both 1s. So your horizontal asymptote is y equals 1, or y equals 1 over 1. We will graph that here. Okay, so what do we know? So we know that the graph has to follow this horizontal asymptote out to the left. As it approaches the right, it has to pass through this 0 here. And if you were to continue further, the graph has to follow that asymptote. Some people will plot points if they're not confident. You're welcome to do so. Like some people ask the question, well, does the graph continue at the bottom down here, or does it continue from the top up here? And there's logically only one explanation. It has to continue from the top, because if it continued from the bottom, it would need to pass through a point
I know
here.
you're in department meetings today, but you can leave at 2:30 because I know you are coming back here this evening for Parents' Night, which starts promptly at 6 p.m. So head out at 2:30. 2:30, and we'll see you back here at 6 or a little before. Thanks. Bye-bye.
You can thank Mrs. Straub for making our videos longer. Anyway, it physically couldn't pass through that point because we found all of the x and y intercepts. So this graph is good, but it's not perfect. It goes back to one last part. Remember we said 3 is not in the domain? 3 not in the domain. Yet I have graphed 3 as a point on my graph. That's actually not correct. All right, I have to fix that. So what I'm going to do is I have graphed 3 is actually not correct there. So what we need to do to fix that is you need to put an open dot right where 3 is on the graph. It means that that singular point is not in the domain, but everywhere else is. All right, for our last slide, we are going to talk about slant asymptotes or oblique asymptotes. And this happens when you have a numerator that has a larger degree than the denominator. Sometimes you get a slant asymptote. Instead of following the asymptotes to the right, to a horizontal asymptote to the right and a horizontal asymptote to the left, it actually extends out at a angle. So what you will see is you'll have graphs, and if you have a slant asymptote, instead of it being horizontal, you will have graphs that could do any number of, like they might follow, they could do pretty much anything in the center, but at the end they're going to extend out in this direction, this slant asymptote. Again, who knows what they do in the middle? There might be asymptote, there might not be, but they're going to follow a slant as they extend right and left forever. So here we will try to sketch a graph doing all of the normal things that we do. Here meaning we are going to find our y-intercept the same exact way. You could try to simplify the top if you see that the top is factorable. If this helps you, you could write it as x minus 2 and x plus 1. Notice nothing cancels out in here, so we can't do the trick like the last problem. Okay, y-intercept is, we're going to do f of 0. That's going to be negative 2 on the top, negative 1 on the bottom. So overall, our y-intercept is 2. Our x-intercepts. I'm not going to go through the work of setting the top equal to 0. I think from the factored form, you can see our two x-intercepts. Our x is 2, and x equals negative 1. X equals 2, x equals negative 1. Both those have odd multiplicity. That's going to help us later. Vertical asymptote, again from the denominator. X equals 1. So now I can draw a vertical asymptote in here. And the tricky part that's new is your slant asymptote. You can get a slant asymptote only when the degree of the numerator is 1 greater than the degree of the denominator. And the only way to find this is to do long division or synthetic division, depending which one applies. So here, synthetic division actually applies. We can use our synthetic division from a couple chapters ago, set up 1, negative 1, negative 2. The number that goes outside would actually just be a 1. And I am curious, how many times does x minus 1 divide into x squared minus x minus 2? That's what this synthetic division question is answering. Bring down, multiply, or multiply. Add, multiply, perfect. What we have left is we have 1x plus negative 2 over x minus 1. This right here is actually the equation of our slant asymptote, but before we're actually going to be able to simplify this equation, because what's going to happen is, as this graph gets very far out to the right, x is going to get very large. If you make this x very large, what happens to this entire fraction? Negative 2 over a very large number is essentially 0, and we can ignore the whole thing. Similarly, when it's very negative, the same follows. So what we really have is a slant asymptote of y equals x. And we can graph that over here. Y equals x is the same slope of 1, y-intercept of 1. There's our slant asymptote. It's saying, as my graph extends to the left, it's going to follow this slant asymptote out to the left. Now, I know it has to pass through this y-intercept. That's an x-intercept. I know it has to pass through this y-intercept, and I know it has to follow the vertical asymptote, so there's not a lot of actual testing I need to do. If you weren't confident in your graph, you could actually plot a few more points. Similarly, I know the graph has to follow this vertical asymptote. I know it passes through because the multiplicity was 1. It's going to follow our slant asymptote the rest of the way. So the slant asymptote only happens when you have a degree of the numerator that's 1 more than the degree of the denominator. You do a little synthetic division or long division, and essentially you can forget about the remainder. You only worry about the parts that are not the remainder. That's the circled parts here, and in this one it's x plus 0. So I hope that helps. We'll go over this more in class next time I see you. Look forward to it. Have a good one.